Hi, Denise. Come up. You want to come up? Nice to see you. We haven't talked for a while. Hope all is well. How are you?
Hi, Katerina. I'm doing great. How about you?
Good, good. Thank you. I will.
Be an exciting talk.
Yeah, it's really cool. I'm so happy that the speaker agreed to come. I'm putting up a Dropbox, and could you check for me if you have access? It
Sure.
should work for everyone, just in case. Thank you.
Yeah, this works.
Perfect. I feel like Dropbox has been improving to share this kind of stuff. Before I think you always had to download stuff, and now they changed that, I think.
That is fortunate. Hi, Wisdom.
Hi, Wisdom. How are you? If you want to come up, let me just invite you. Haven't talked with you in a long time, too. Nice seeing you. Yeah, guest speaker has never been on Clubhouse before, so yeah, the first few minutes will explain a few things.
It's always sort of fun when they've never been here before.
Yeah, I agree. I like it too. How's been the new year treating you? All good?
Yeah, it's been, can't complain too much.
That's good.
How about you?
Yeah, the same. Like, I can't complain too much. It was good. It was cold, now it's kind of warm again. It's the only worry I have, that it's not winter really anymore here in New York.
Yeah, it snowed twice since I've been here.
Oh, did you move or?
Yeah, temporarily.
Oh, nice. Yeah, but it was just tiny amount of snow, like really just
Like an hour.
like nothing. Sure. Yeah. So I don't know. It used to snow a lot. And
Yeah, that's exactly. I mean, I landed here in January. I was like, "Where's the snow?"
yeah, last year was the same. It's not a little bit. The years before, we still had a few, not that much like it used to be, but still snowstorms. But now, since last year, I feel they are gone. Yeah. Hi everyone. I shared the lab website in the chat, and then the paper is open source. It's Nature Communication, and it's also there for everyone that wants to read a little bit. And then the slide presentation is pinned on top. So yeah, should be really interesting. I'm really looking forward to this discussion. And yeah, the guest speaker is new to Clubhouse, so bear a little bit with us. We'll be fine. So,
Starting at the top of the hour, is that right?
yeah, exactly. We'll start on top of the hour. Feel free to share the room. And yeah, we will begin shortly. Let me see if I can find our guest.
One question I'm looking forward to asking the presenter is, what is the largest object they've moved for the longest duration?
Yeah, that's a cool question. That's definitely on the list. Yeah, you should ask that. Well, definitely.
Sure will.
I feel like we're on the brink of beam me up, Scotty, but probably not. Well,
That'll definitely. I'd love to hear you ask that question. How far are we from this?
Well, it was always my dream, you know. You probably know yourself, like as an immigrant kid, you have to travel a lot throughout the year.
Mm-hmm.
And I always wished, oh my God, I wish I could just, you know, do this faster, just beam me, beam me to, you know, home and back. So, you know, instead of having.
You probably have seen this. Um, there was a story about how I think it was NASA was able to um, move matter. I think it was matter. It was like a very tiny amount, and it was only from one point. I want to say one point on Earth to another point on Earth. And it wasn't like a really long distance. It was less than, I don't know, 100 kilometers or something like that. But they were able to do it.
Oh,
Have
there's,
you?
yeah, I read that too. Hi, Ognjen. Ognjen. I'm sorry. Am I saying your name right? And I checked on your website this morning because there's a very convenient play button to play your name, but I already forgot. I'm so sorry.
No worries. Can you hear me?
Yes, perfectly.
Okay, yeah. So my name is Ognjen. I go by Augie as well, which is much easier.
Okay, Ognjen. Ognjen. I'm sorry, Og. Thank
No
you so
worries.
much. Thank you for coming and making the account and taking the time to come here. We are already very excitedly speaking about sci-fi type of, you know, usage of this technology, which
Uh, no, excited to be here and tell you more about it. I don't know how much we can maybe, let's say, um, avoid the disappointment of some of the things that can happen in science fiction that cannot happen in our research, but some of the things can have very nice analogs. Maybe let's put it that way. But so I'm very happy to tell you more about the work that we do and why we find it so exciting.
yeah, definitely. No, you will definitely not disappoint at all. We were just, you know, speaking about the imagination in a fun way. So, um, we will slowly start. I know it's a little bit early, but we can, I think, start with introductions and so on, and then we'll do a short interview section before it's, you know, time for presenting your slides. So, and for everyone, the slides are pinned on top of the room. Everyone should be able to access them. I shared again the paper on in the chat, and it's open source, so everyone should also have access to that. And then I also shared the lab website. Please check it out. It's really interesting to learn more about the lab. Yeah, I think we can start. And yeah, please meet Dennis. Dennis, um, uh, we are very excited to start.
Wonderful. Can I ask a quick question?
Oh,
So I
sure.
realize my slides are in PowerPoint, but if they're being I don't know if you're scrolling them online. Maybe I should have uploaded them as a PDF. I know sometimes there's, you know, like the transitions that PowerPoint can do if it's kind of shown in a browser of Dropbox might not work. So I would just have the question about that.
Oh,
Uh,
the
if
transitions you mean when you make like from one slide to the other and the graph pops up or something like that?
Sure, like sometimes animations, and I think there's a couple of videos. I don't know if they would show in
Mm.
a browser if they're open um, through Dropbox directly. So that's kind of my question. I'm not sure.
Um, yeah, if it's through Dropbox directly, let me check again. I think it worked for me, but I could have just have. It's
Maybe
okay.
technology is getting better
Also,
and better.
I know that videos don't work anymore on Google Drive, they used to work for a while, and then we had to kind of switch. No, it works. I see it popping up. Yeah, it's
Okay.
fine.
Oh, I think that's working.
Yeah,
Okay, let me see if the videos will work.
for me it will work. The videos on which
Mm,
slide?
they don't, a 12, I don't think they work.
No.
That's interesting.
Okay.
Um,
Oh, I'm sorry. I didn't realize. So for everyone that wants to see the videos, please uh you could send me really quick the videos and I can upload them on Google Drive and share them, or people just have to look at the slides on PowerPoint instead of in Dropbox. So I think most people are fine with doing that. So
okay.
yeah, good. So well, thank you so much for coming. It's a great honor having you here, and we will start with a short introduction so people get to know you a little bit better. And then we'll go from there. So, Dr. Ognjen Ilic, he has the laboratory for nano optics and mechanics um, at the University of Minnesota, and he is a Benjamin May Huge assistant professor at the Department of Mechanical Engineering, and he is also faculty of the School of Physics and Astronomy and Electrical and Computer Engineering. He did his PhD at MIT at the Soljacic group. I hope I said that right. At Harvard University, and he then did his postdoc at Caltech at the Atwater Group, and he won several awards: the McKnight Land Grant Professor, Air Force Young Investigator Program Award, the 3M Non-Tenured Faculty Award, and Materials Research Society Bulletin Prize Whitman Fellow at MIT. And we usually do the rest of the introduction kind of through a short interview, if that's okay with you.
Of course, yeah.
Perfect. So our first question is, when did you realize you wanted to go this path and down this path to become a scientist? Was it something you always dreamed of? Was it something that came maybe later on by reading a book or a professor or a class you took? Maybe parents pressured you, whatever the answer is. I think it's really interesting for non-scientists and for young people that are starting their career to learn about that. Thank you.
Oh, that's a great question. Let me see if I can trace it back. I'd say probably my first exposure to physics was just something that really impressed me, kind of the ability to describe how the world operates, but in such very simple terms, right? If you think of something like Newton's first law, like and secondly, force equals mass times acceleration, we can use these very relatively simple concepts to, calculate the trajectory of a rocket. So that simplicity and how much you can do with it, that's kind of embedded in physics, is what I always found really extremely interesting. And I have enjoyed doing physics and math kind of through early education in high school. But I'd say really in college, I saw that as a career path, kind of seeing professors that could do very interesting research and teach on these subjects, and I saw myself really being interested in doing that. And then that kind of continued through graduate school, postdoc, and now I'm really happy to have the job that I have. I think it's certainly the best job I can imagine for myself, and it's really enjoyable. And I think something that's exciting about this work is that you really never know what you're going to be working on in a few years, right? I can't necessarily know what I'm going to be working in 5 years, and that's just really incredibly exciting. Um, so maybe that's a short answer to that question.
Yeah, thank you so much. It's an interesting answer, and especially the part that, you know, we never know what we will be working on the next years. It always depends on, you know, the results and the current ongoing research. I think that's a really wonderful mindset. And do you think you need that mindset to make major discoveries like you do? Because I would say there's also a lot of research that stays on the safe side, maybe with a different mindset. I don't know. We ask that question here sometimes. What people think, what the major, what the ingredients for such a major discovery are. Um, thank you.
Yeah, so that's a really great question. I wouldn't say that it's a required mindset. I'd say that it's just a really fun way to work. Um, yeah, I don't think I certainly never think of it as my goal to, you know, discover something amazing. It's just really finding really interesting phenomena in different systems and kind of using what we know in one system and seeing if it would apply to a different system. And for example, here what I'll talk about is my background and training are really in optics and photonics, and we kind of saw how some of these ideas really carry very nicely into acoustics, even though we basically didn't had done no research in acoustics before. So I'd say it's a really fun way to work, um, and uh, and then sometimes things work out, sometimes they don't, but um, yeah, there's definitely not as much pressure and much more enjoyment when kind of trying to think a little bit outside of the box, and kind of seeing where our skills translate. Um,
Yeah, thank you. And then how did you alluded a little bit to that nobody else was really doing work in this field. So how did you come to work on this project and start this endeavor? Thank you.
Yeah, so maybe I'll kind of clarify. I'd say that certainly folks have been working, and I'll talk a little bit, in my slides that on different ways you can use uh, like light or sound to move and manipulate objects. What I meant to say is that uh, some of our research was predominantly in optics and optical materials, and when we saw some really new ways of doing things there, we then thought it would be interesting to apply this to systems we didn't know much about and kind of found, let's say, some low-hanging fruit that maybe others have missed. So that's I would say that connection that led us into this paper and the research that I will talk about. And I think maybe from the slides a little bit clearer about kind of what the state of the art is or was, and kind of some of the ideas that we were excited to test out in the systems.
Wonderful. So, yeah, everyone, the slides are pinned on top, and feel free to access them. If you want to see the videos, please access them through a PowerPoint. And yeah, the stage is yours. Thank you.
Thank you so much. So maybe let me, so would I kind of let folks, what is the best way to kind of sync the going through the
Yeah,
slides? Do I kind of tell folks, so now move on to slide two,
yeah,
or what is, how does this?
that would be best, I think. Exactly.
Okay, so let's see if how this will work. And I'll obviously take suggestions from the audience if it's the first time I'm kind of presenting with instructions as to how the slides should move. So I know we'll give it a shot. So maybe from the top, I can to start, I'd say that I'm very happy to be here and tell you about our work. And the title of this discussion is Metamaterials in Motion. And in a second, I'll explain what I mean by metamaterials, but maybe the main takeaway point I hope to make here is how we can harness the energy and momentum of waves to move objects without physical contact. Uh, So now moving on to the next slide, a brief introduction. I am an assistant professor of mechanical engineering at the University of Minnesota Twin Cities, and I'm really fortunate to be part of a wonderful team of undergrads, grad students, and postdocs um, that come from very different educational backgrounds. So we are a mix of physicists, material scientists, mechanical engineers, and electrical engineers, and also from uh, uh, you know, many different places around the world. But what unites us, I'd say, is a really shared enthusiasm for understanding how waves, especially light and sound, interact with materials and metamaterials, and how we can understand, design, and apply those interactions in different areas of energy sensing and robotics and so on. So maybe we'll move on to the next slide. And kind of before I tell you about what our goal is, maybe the general kind of background to motivate this work of manipulation or contact field manipulation is to say that really across many areas of science and engineering, there is a universal need to actuate objects. We want to translate a signal into controlled motion. And often we do this by means of physical connections and tethers, and the energy for that motion can be delivered externally. For example, a robotic actuator arm that's connected with a wire, or carried itself by the moving object, like a battery. A drone would have a battery, and we can control its motion. But what would be really interesting to achieve is the ability to move objects remotely from a distance without contact and without an onboard energy source, such as a battery. And this is something that waves can provide. They have these two distinct qualities where this manipulation can be contactless, and we also wouldn't need an energy source to do it. So now the schematic that you see here kind of envisions how a wave, for example, an inaudible acoustic wave like ultrasound, can impinge on an object, and we would like to move it in the desired direction. So now I think if you go to slide 4, I think should pop up on the side that kind of explains what we want to have on the surface of that object. And we would like to essentially pattern a deliberate and precise set of features in the surface that allow us to change, kind of control how a wave scatters off of each point on the surface, allow us to control the force and the torque, and then really enable us to develop new actuation dynamics on these objects. So now slide 5 kind of brings our kind of the work that I want to tell you more about, titled Shaping Contactless Radiation Forces Through Anomalous Acoustics Scattering. So what the schematic of the object on the right is what we call a metamaterial and a metasurface. And on slide 6, it's worth giving a very broad definition of what a metamaterial is. And these are subwavelength-structured materials that combine geometry with material properties to control the response of that object, for example, reflection, transmission, absorption, emission, or scattering, in ways that is not possible with natural materials. So we want to combine essentially geometry and material properties and do something that we cannot do simply by the chemical composition of that material. So an example of that has been kind of interest in both optics and acoustics in the last few years is the ability to design new kinds of devices using these principles. So on slide 7, we talk about the difference between a functionality derived from a macroscopic shape of a material. So if you look at on the left, you see a conventional lens, and the lens works like a lens because it has this macro scale shape to focus light. But on the right-hand side, we can essentially mimic that functionality in a metasurface lens if we deliberately control the pattern on that flat surface to mimic the same scattering of waves. And then I think the bottom of that slide shows really the phenomenon that underpins this. On the left-hand side is something that we know as Snell's law. Snell's law tells us that if a wave impinges on a surface, it would be reflected at the same angle that it is incident. And a generalized Snell's law on the right shows that by controlling the patterns on the surface, we really can program the direction in which that wave will scatter. And in doing so, we can realize all these rich functionalities such as steering beams, focusing beams, and also controlling mechanical actuation. So with that in mind, I wanted to kind of set the stage for what is kind of the current state of the art in contactless actuation and how we are hoping to push that, push those boundaries. So on slide 8, on the left, you can see something that it's called an acoustic levitator or an acoustic tweezers. And here, a collection of ultrasonic transducers, you can see on the top and the bottom, generates a standing wave profile where we can trap and manipulate small objects, right? So this is the acoustic tweezers and traps, and they've been used in many different areas of microfluidics to manipulate small droplets, to understand their properties, to manipulate small insects, small biological objects, and so on and so forth, right? So the domain of acoustic forces and acoustic levitation is pretty pretty rich, and there's a lot of research in this area. So these are pretty interesting. It's actually not too hard to put one of these together, and we can really make very compelling scientific demos, especially for public communications. But there's some intrinsic drawbacks in this conventional manipulation. So if we look on the right, really in this way, we can only trap objects that are smaller than a half of the wavelength of sound. And that's because they need to fit into the nodes of the standing wave to be trapped. And typical transducers might be on the order of 40 kilohertz used here. And if you look at the one half of the wavelength at those frequencies ends about 4 millimeters. So this is why these objects are generally small, and also the manipulation, the distance of manipulation is generally it's a short range effect. So with that in mind, we can now go to slide 9. Our idea was to try to see how we can engineer different dynamics, whereas instead of trapping small objects, we'd like to look at bigger objects, but objects whose surface is patterned in a very deliberate way. And again, we would like to pattern the surface to control the scattering of waves, and in doing so, engineer forces and the dynamics. And then in this paper really showed 3 different effects. Effect A, that this is possible, and then effect B was shown here, where we would like to guide an object autonomously, right? The idea was, can we design an object such that it would follow the source? So if a source moves, source of the wave moves, the object would autonomously want to go in that direction. We call this autonomous self-guidance. And then the phenomenon C we were curious to design is negative forces. This is also not negative forces because they're they pull the object towards the source of the wave, and that's essentially what a tractor beam is. And this is definitely possible to do if one can engineer this object to have stronger forward scattering, then the net force on the object will be backwards. So I'll take a little bit of time to kind of guide through some of these phenomena. So on slide 10 is an example of how we design these metasurfaces or metamaterials, and they typically consist of a unit cell that you can see on the right that is repeated in some controlled fashion across the object. And The synthesized structure is designed to operate for 20 kilohertz. It's just above the audible range. And you can see a dime here for scale in this image. And this object will take incident sound at 20 kilohertz and it'll scatter it strongly in one direction, which means that the force that it'll experience by Newton's law is going to be opposite from the scattering. So we were excited to test this out. So on slide 11, you can see our measurement setup where we take a set of these transducers. They're relatively weak sounds of source, weak sources of sound, the intensity is relatively low, and we mount one of these metasurfaces on this suspended system. And we can see that once we turn the sound of source on, this is on the plot to the right, this object starts to deflect, and we can measure the deflection optically by moving mirror, which is not shown here. So it kind of assumes a new position, and then once we turn the sound off, it relaxes back in its original state. And really a video on the slide 12 shows this phenomenon, but I guess that we can't really, so I don't know if I should maybe pause here for a moment to let folks play the video or maybe move on. I don't know, Katerina, if you have a suggestion.
How long is the video?
It's about, let's see, 10 seconds. I think it's pretty short. So I think once you play it, it just shows how this, once it has a little green on sign that turns on about 3 seconds in, and then you can see the object starts moving.
Yeah, I saw it. It looks really cool. Yeah, thank you. I think.
Okay. Okay, I think I can maybe move on to the move on and then.
Yeah, I think. Thank you.
Okay, sounds good. Yeah, so this was kind of the first phenomenon. So we saw like, okay, we can engineer these forces, and then what are some of the interesting things we can do with it? So now on slide 13, we talk about the concept of autonomous self-guidance. And the idea is, and you can kind of see it on the left, is we would, if we don't have an object, we create, this is a simulation result, we create a focused sound field. This is again 20 kilohertz, it's inaudible, so we can't hear any of these effects. And then if we position an object in that field, and we try to move the source in one direction, the object scatters waves in a way that it'll want to follow the source. And this is kind of embodied in this force profile that's shown on the top right. And you can see that if the source position is positive, say for example 25 millimeters, the lateral force in the object is also positive, which means it wants to follow in that direction. And if the source position is negative, the force will be negative. So this is the kind of behavior that we would like to get. And we synthesized our first design and then fabricated this metasurface that is shown in the bottom right. Again, a dime is shown for scale. So obviously, then let's demonstrate that effect. So here is an example on slide 14, where we have the measured results on the left and kind of the schematic of 3 different positions on the right. And our source, which is the red dashed line, will first move in one direction. This is the positive orientation, and then move in a different direction. Displacement of the object will first follow the source and then follow the source in the opposite direction. So the images for the, say, minus 15, 0, and 15 degrees are shown on the right side of the slide. And then the actual video is shown on slide 15. So here I'll maybe pause for about 10 seconds again that shows these sped up video of how this object follows the source, the green source that is underneath.
Yeah, I see it. It's really following it.
Yeah, so the distance is about 10 centimeters between those two. So we programmed the stage that takes the translational motion into rotational motion of the source, and then this object on the top follows it. So this kind of shows that it'll want to stay pinned to this beam axis. Now moving on, our third effect was the negative forces, or really tractor beams. And we wanted to demonstrate this in what we call reflection mode, and that's schematically shown here. If the wave comes at an angle, and we design the structure to kind of have this sequence of red arrows that you can see here, where it'll take wave at an angle, scatter it forward, the net momentum change will be such that the force will be towards the right side of this plane, meaning towards the source. And we have again a fabricated metasurface here, and our predicted result from simulations shows that for this object up to about maybe 25 degrees, we should be able to feel these attractive forces, or these tractor beam forces. If the angle at which the wave is incident becomes higher, then it starts pushing this object. So there'll always be a kind of a trade-off between the angle at which the wave is incident on this object and whether it is a pulling effect, meaning a tractor beam effect, or not. And then in slide 17, we have the experimental results. It's slightly, we showed that the pulling can be true to about 22, 23 degrees, and you can kind of see the experimental setup image on the right, where you kind of come at an angle, and we saw that up to a certain angles, this object will move towards the source of the radiation. That indicates that this, at least in this first attempt at strong forward scattering, the effect is there up to about 23 degrees or so. Okay, and then I'll talk a little bit about kind of the things that would be really interesting to do in the future and what we would like to do next. And that's on slide 18. So really the next concept would be to realize this metasurface levitation, right? As I mentioned, conventional levitation has the challenges that it typically applies for small objects, whereas if we were levitating metasurfaces, we could design them to induce self-balancing forces and torque such that they can actually stabilize themselves in a sound field without needing to be very small to be trapped. And then it would be very interesting to try to scale the concept. For example, scaling this to higher frequencies, meaning shorter wavelengths, could result in much smaller objects, potentially objects that could be, embedded for applications in, cargo delivery or soft robots and so on. And also examine applications in picking and contactless picking and placing in, say, environments where materials are delicate and cannot be physically handled, potentially sensing and imaging of large levitated objects with omnidirectional access, and so on. And then here, I don't know how I'm doing on time, but I think the rest of my slides look at the same ideas for light and some applications that could result from that. But maybe I'll pause here and kind of check how we're doing on time, Katerina.
Oh, it's fine. It's 3:30, so we still. I mean, it mostly depends on you how much time you
Yeah.
still have with you.
Well, I think probably just a couple of minutes. I think the parallels are really interesting, and I think it would be, yeah. Let me do that. I'll just.
Yeah.
I'll take a few minutes to talk about the optical equivalence of these phenomena. And that starts on slide 19. And the reason why I think that's really interesting is because optical manipulation is a very widely used phenomenon. So in 2018, the Nobel Prize in Physics was awarded to Arthur Ashkin for his discovery and invention of optical traps and in the 1970s. And this is a schematic shown in the bottom left that shows if you take a laser beam and you focus it very tightly, you will create a region in space where small particles like nano and microparticles can be trapped. Uh, 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 and this idea is really, I would say, probably one of my favorite concepts in physics, because it really feels like straight out of science fiction that you can trap small objects and essentially in midair. And optical traps and tweezers have had numerous applications over the last 30 years or so, 30, 40 years. In cell biology, for example, in studying the biomechanics of DNA, optofluidics, colloidal science, microchemistry, and so on. These are really very versatile tools. But then if you go to slide 20, this still has been really restricted to nano and microscale particles. We do not necessarily see this macroscale phenomenon of optical traps and optical tweezers. And the reason for that comes in the dynamics of that trapping. So that's in slide 21. Similar to acoustic tweezers, objects are trapped because they're very small and the beam of light is very tightly focused and essentially creates this spring, this intensity gradient spring that can trap small objects. And then on slide 22, you can kind of see it more realistically what that looks like. We take these very high numerical aperture lenses and really in very close proximity can we create these conditions that can trap objects. And for that to be true, it has to be very close to the lens and it has to be very, very small objects, typically nanoscale or microscale in size. And then on slide 23 is really the same ideas but applied for light, where if we now start look at macroscale objects, but we pattern their surface in the right way, we can realize the conditions for stable macroscale levitation. And this is some of the ideas in optics, some of the papers that we have published on that in that front. And then this idea to control objects can apply not just on a nanometer scale object. This could be millimeter size objects, potentially even larger than that as well. And then I'll conclude with a slide 24 for some of the really interesting uses of macroscale levitators, and one is for sensing applications. Levitated objects don't have any tether, so they're decoupled from environmental sources of noise, and they could be very precise ways to measure forces, for example, gravitational forces. And then there's also some really visionary and interesting applications for moving objects in space. You do not need, you can't use sound in space because it needs a medium to propagate, but you can definitely use light. And there are these really interesting concepts such as solar sails that NASA and other space agencies are actively developing. These objects use the energy and momentum of sun to move in space. And we can think of essentially embedding these metamaterial metasurface structures to really control the trajectory of these very large sails. And this also doesn't have to be just driven by sunlight, it can be driven by laser light and then allow us to really move objects in space much faster than any spacecraft that have to carry their own fuel, right? It'll essentially allow for fuel-free propulsion in space. So there's some of the very interesting concepts in some of the papers by us and other active groups in this area. So I'll stop here, slide 25, kind of thank some of the folks that fund this research. But yeah, I would love to continue this discussion, answer any questions, and yeah, thank you so much for your attention.
Thank you so much for this wonderful presentation. This is a really fascinating how this designing of this meta surfaces can lead to this very precise control with the incoming wave patterns. Yeah, I was thinking about the microbots controlling immediately because we had a few talks before of speakers that talked about nanobots and so on fighting bacteria. The thing is always, how do you control them well to where they should move and so on. So with these wavelengths that you're using, if you're in an organism like a human, how deep can you go into a tissue and stay precise? Did you test that?
Yeah, so this is a really interesting question. Is how it kind of goes back to some of the interesting areas for future work is how does this concept scale down or scale up in size? And if we're looking to embed something, say in a biologically relevant medium, we would want to ensure that there is sufficient transparency of that medium to the ways that we want to use to send this energy and the signal through, right? So in the case of optics, we might want to operate in the biological transparency windows where your light can actually make it through. Or in the case of ultrasound, we also want to make sure this is done at the right frequency, such that the skin and other tissues that are in between don't attenuate the signal too strongly. And then there's also a question of whether we are using these effects for actual movement or we use them for steering. And that can mean two different things. Typically, if one wants to move something, one is fighting, the inertial or potentially viscous resistance to motion, and you'd need more energy to achieve that movement. But if you're just looking to steer and then use a different effect for movement, for example, a so let's say we have, I'm just thinking like, it's like a soft robot that is, propelled through a fluid mechanism, and the fluid can have a lot of power, uh, and one is then interested in steering that object, kind of sending the steering signal. Then the steering torques, for example, could be done in this fashion, whereas the actual power for motion comes from a different mechanism. So those are some of the open questions of how this can be scaled or embedded in a medium and still remain and still be an appreciable mechanism.
Yeah, thank you for the distinguishing between the steering and the actual movement. That's an interesting um, detail that I didn't think of before. And then when you talked about the metasurface self-guiding part, so you have the self-guiding structure, basically metasurface structure pattern, but the source position then is still has to be quite precise then still, right? As if I understand it right. Or can it self-guide, like does the source position has to change and then kind of basically it's a feedback loop mechanism for self-guiding?
Yeah, so that is a great question, right? So the general, when we talk about self-guidance, there's going to be some relevant time scale. And that has to do with, if the source moves too fast for the object to follow, then this would not be possible. And that, for example, could be if the object is in a very viscous medium, and the object can. For this to be true, the object needs to experience a uh, changing field from the source, right? That's what kind of makes it possible that if the object is locked onto the source, it doesn't experience any, it's kind of in equilibrium. But if the source moves, um, the object sees an asymmetric field profile and tries to restore that to the equilibrium position. But if the source moves too fast before the object has had a time to respond to that, then obviously it'll kind of be lost. Um, uh, it will not have, it will not be able to follow it. So I think the dynamics of self-guidance will depend on A, how fast the source should move, and then B, what is the medium in which the object is trying to follow the source, and whether there is, resistance to movement that can slow this dynamics down, and then the object wouldn't respond. So it kind of is, you use the right feedback concept. It is almost if one is trying to control a system, but the feedback is too fast, then the object doesn't have time to respond to that, and it kind of is not controlled. So this is the exact equivalent constraint here.
Yeah, thank you so much for that answer. And I wanted to check with Dr. Shah and Denise if did you have questions? And please go ahead.
Yeah, thank you so much for your wonderful talk. So my question, it might be a little bit strange. I don't know exactly about it. Is about the memory cell, and is that possible that we use this kind of method for the kind of producing nanomemory or mimicking the brain kind of long-term memory producing or not?
So that's an interesting concept that I'm not very familiar with, but maybe if what I'm kind of hearing, the question is, is there a way that we could remember, encode emotion, and then try to realize it later to some extent?
Exactly,
And
and it can be muscle memory as well.
correct, yeah. So that's really, I think in this, maybe let's say a linear regime. So this is, we would say that this is, a linear wave physics, in the sense that um, the response to waves is linear. I would say probably not, but if one starts incorporating nonlinear materials, or a way to store the energy, uh, then that could potentially be possible. So maybe if this is, say, a very soft material that experiences a certain um, uh, you know actuation or profile of forces and torques, uh, twists itself in some shape, and then when exposed to a medium of the right, I don't know, chemical, biological properties, can perform some, remembered motion. I mean, that sounds all very interesting, and probably be possible, but probably would have to be the right material base to do that. These kind of rigid objects that operate in a linear fashion would not be sufficient, but there could be other material platforms where that is possible.
I see. So I think that we should think about the bionic or those kind of things if we want to think about that.
Yeah, no, certainly very interesting to think of how, you know there can be a, time scale to store energy to then have a, programmable or controlled motion at a later time.
Or digital memory can be another kind of possibility.
So maybe it would, kind of to kind of think very broadly, this is all done with materials whose primary response is meant to be acoustic. One can think of combining, say, optical, acoustic, or electronic properties of materials to do something, much more complex than simple motion. Um,
Thank you so much.
no, thank you for your question.
That was a really interesting talk. I have a couple of questions. What is you had mentioned that these are very small objects, so I was just curious what the largest object that was moved in this experiment was, and what was the distance?
Yeah, so these are size, I guess, so I'd say when it comes to, metamaterials, they could be, depending on what wavelength regime some operates, folks would say this is a big object or a small object. These are, if I go, come back, let's say maybe slide 10 or so, these are on the order of, let me see, I'd say probably about 12 millimeters thick, and then maybe about, you know, 5 or so centimeters across. So they are, you can certainly hold. I mean, we 3D print them, so they're big enough. And the reason they can be so big is because the wavelength of sound we used, ultrasound, which is 20 kilohertz, it's kind of right at the audible, the edge of the audible range. That wavelength is 17 millimeters in air, right? So we essentially want to have objects that are bigger than the wavelength, and they are. They're about several wavelengths across. We wanted to make them bigger than the wavelength to kind of demonstrate that this can be done for large objects. But their surface patterns are, I believe, the smallest feature size on the order of maybe 400 microns or so. So they are the size of the objects will really depend on what wavelength one wants to operate at and what one wants to do with those. The very first thing we wanted to do is just to demonstrate this concept, and we wanted to pick this 20 kilohertz wavelength to make it. They make them. Um, so it's a nice balance between not being able to hear these sounds, so that you wouldn't annoy your colleagues and coworkers. Um, but if they're too high in frequency, we can't really use a regular 3D printing because the feature sizes have to be very small. So at these ways, we kind of hit the sweet spot of, our first demonstration can be done with something that we won't be able to hear, and we can easily 3D print. So
Got it. Yeah,
this
there's a balance
motivates.
there, huh?
There's a balance, right? Because if you want, you can certainly make these things bigger, but then you're getting into the audible range, and then you'll start hearing these transducers, and that might not be a great thing. But then if you do something like 40 kilohertz ultrasound, your features have to be now one half the size that they used to be. So the objects can still be 5 centimeters, even 10 centimeters, but the feature sizes have to be smaller. And it just kind of, we start getting into this not as easily 3D printable regime.
Well, I mean, 5 centimeters isn't small when, it's about 2 inches or so, right?
Mm-hmm.
So that's pretty large. I mean, that's when I'm thinking about this, another part of my question was going to be about medical uses. This definitely seems like it falls within the size range. I don't know. Obviously, ultrasound can penetrate human tissues. I don't know to what distance, the performance starts to degrade. But there we've had speakers here that have presented regarding magnetic manipulation of medical devices inside the human body. It sounds like. Do you see any application for this technology within the medical realm?
Yeah, so I think just to when you say 5 centimeters, there's let's say kind of two length scales that one has to keep in mind. So if one first selects the frequency they want to work at, let's say 20 kilohertz, that has a wavelength of 17 millimeters. The patterns on the surface of the object have to be, much smaller than that, right? So
It's like a sail, right? Like a sail on a sail ship trying to catch the wind.
So kind of think of it. There would be patterns on the sail, right? So the idea is, let's say you could have the sail can be any shape, but we're essentially putting tiny little stitches on the sail. Maybe that's the way to put it.
Surface texture.
Surface texture, right? So the surface texture has to be much smaller than the wavelength, right? So this is
So
what
that
I
it can
meant.
catch this ultrasonic wind.
That it can catch it, and that it can at each point program the pressure independently of the points nearby, right? So it's kind of, imagine that at each point on a sail on a boat, you would be able to exactly design what the force that the sail experiences is, right? So we can't, because our sails are kind of, not necessarily textured, but the point of a metamaterial is that we can kind of really along it precisely at each point on the surface control what the force and the pressure is felt. So that's what's limited by how small you can print features. But the actual object, going back to 5 centimeters, we actually wanted to make it as large to show that this limitation of only manipulating small objects with sound really doesn't apply anymore. We want the patterns have to be small, but the actual size of the object and even the shape of the object no longer matters. Um, so this is kind of, and maybe the way to communicate that message the best is kind of the three demonstrations that I talked about, you know, um, kind of, metamaterial force or self guidance or tractor beaming. If you look at the shape of these objects, they all look the same. They're just rectangular prisms. They look like 3 blocks, right? On the order of about 5 centimeters by 1 centimeter thickness, right? So if you just kind of, you know, but the actual patterns are very, very different, and it is those patterns that give the different functionality to this object. And kind of going back to your question about in medical applications, certainly if this can be scaled down, for example, if you want to embed something, you can maybe operate at much higher acoustic frequencies. These objects would be smaller, and then you would have even smaller features, and then you could use this to guide things and manipulate and potentially even steer them in for biological application. Does that answer your question
It
in
does.
terms of kind of the difference between, we need our patterns to be smaller than the wavelength, but once we can get the patterns to be right, the actual shape and the size of the object really doesn't matter.
As long as the wind, as long as the sail can catch the wind, it doesn't necessarily matter what the sail's shape is. So I was curious.
Correct.
You're probably not using PLA plastic. What are you 3D printing with?
So this is just conventional, I believe, polyjet 3D printing. And I don't exactly know the type of thermoplastic that is used for this, but our minimum feature sizes at these wavelengths had to be, I believe, at about 300 to 400 microns, so 0.3 to 0.4 millimeters. And that is certainly within the realm of, conventional commonplace 3D printers. Obviously 3D printing can work even in much smaller scales, but there's a trade-off of, then the cost and the time to printing can take longer.
What model of printer are you using?
So we both printed these using some of the in-house facilities in some of our common centers, and we just kind of send the designs, and they would return back to us here at the University of Minnesota. And we also use some external services, companies where you can just send them the CAD files and they will print. So we kind of had to iterate a couple of times to get these things to work well.
Mm-hmm.
I don't
So then
exactly know what models of printers they use.
Okay, that's fine. That's a detail I thought might have been too far. But have you tried different sorts of printing mediums, like as in the material that's being extruded?
That's a great question. We did so. From the point of view of their acoustic properties, if they're solidified and rigid, they have relatively similar acoustic properties. I'm going to kind of put relatively in the quotes here, or similar. So we didn't really bother to test different materials, but certainly if they become more porous or soft materials, they would have different properties, which could be a good thing. But we, for our initial demonstration, just looked at, standard solid things, and maybe to folks in additive manufacturing, saying standard solid materials doesn't mean much because that can mean many different things. But for us, it kind of, as far as the acoustic properties meant, there was not that much difference. In our simulation, we would see that really wasn't that sensitive to the choice of a thermoplastic.
Well, I suppose there's certainly room for further experimentation in that particular fields of materials. So I'm curious, what are the goals? What is the, are the goals in terms of like largest object move for largest distance, or like what are your future goals for this sort of project?
So I think it's a great question. I mean, maybe I can tie it back to some of the earlier slides. When we want to move something, we would like to be able to take an object and move it in any position in space or with any orientation we would like, right? So now we can break down what are the functionalities needed for that. Well, you need to be able to steer an object, right? So you need to be able to translate the energy and the signal for moving in different directions. They would potentially have to be completely opposite directions if you're steering or rotate things in a different way. So not just forces, but also steering torques. You want to be able to not just push objects, to maybe pull objects. So kind of, if I think of point A in three-dimensional space and a point B, and I think of all the motions, the building block motions that I need to be able to get from A to B, we still don't have all those functionalities at all. We don't necessarily know how to steer, how to orient objects in this fashion. So we would want to be able to develop kind of the physics, kind of the wave physics that gives us that functionality. And then, as you mentioned, it really comes down to then applying this to different systems, different materials the objects can be made out of, but also different media the object can propagate through. And that kind of takes the idea of moving from A to B of different objects and different materials. This becomes there's a lot of, certainly for the near and the midterm future, there's a lot there to unpack. Whether it's done in water, done in air, or in a different medium, done with soft materials, rigid materials, and so on. So this is just kind of a first concept demonstration of something that was relatively easy to do. I probably suspect, the next work to have its own challenges.
Surely. And so these experiments were only in the air? Sorry, last question, Katerina.
Correct, only in the air. Yep, this is all in the air of rigid objects, right? So we kind of just have one data point in this kind of material medium design space.
Hey, we need proof of concept. Really appreciate your work. Thank you.
Thank you for your questions.
Yeah, thank you so much for answering all the questions. As going back to what we were already imagining, like some future transportation device through long range and all these things. So it's for sure an interesting new field I think you created there that will have a lot of applications from the very small scale up to very large scale. I mean, if you can have these autonomous moving controlled objects, you could think of long range transportation also in the future through, I don't know, could you use the current radio towers to control those and the frequencies?
Yeah, that's a great question. I think it'll come down to the frequency, but also the intensity of the waves or radiation. When we speak of the intensity of waves, we think of it as radiation intensity. A lot of times communication intensities need to be much lower. Again, depends on the distance at which one wants to communicate and the kind of the bandwidths and that one wants to transmit. So probably it will come down to having enough intensity in these waves to do this. In terms of the radio waves have very long wavelengths, so they wouldn't necessarily be the right kind of waves, right? This could be, kilometer long wavelengths. So, to be sub wavelength for a radio wave, it's essentially, you could have, a car would be sub wavelength for a radio wave. So probably, but certainly other kinds of waves, whether in optics or acoustics, sorry, same waves but at different frequency regimes, the wavelengths could be relevant. But yeah, it'll come down to both intensity and also how collimated these waves can be over long distances, right? That's something that's exciting about optical manipulation with lasers, that a laser beam can stay collimated over very long ranges. So in principle, we should be able to levitate objects, maybe not big objects, but objects certainly bigger than microscale and microparticles over long ranges, because laser beam can be collimated over very long distances. So I think if that can be done, that would be very exciting.
Yeah, I was thinking about the helium balloons or transportation that some companies in Europe now are restarting for long range, not necessarily fast transportation, but of long range, more renewable energy type of transportation objects. And if you could make those helium, like big helium balloons, structured with the right metasurface, if you could basically make like a autonomous air streets with stuff that you frequently have to move back and forth between places. But maybe that's too far off.
Yeah, I don't know much. I mean, I think at that point it was also kind of the aerodynamics of these objects and kind of the actual flow of fluid, not just, sorry, the air currents around it would be a big part of that, of solving that. So I'm kind of hesitant to speculate, to go too much into things I know really very little or nothing about.
Yeah, okay. I understand. It's just my imagination going on. But yeah, we talked an hour, so thank you so much for coming here and um, really presenting this really amazing research that you're working on, which is so interesting, and we will be curious to follow it in the future. For sure, a lot of more exciting um, science news will come out of your lab. So thank you so much, and yeah, maybe we'll hear each other again in the future about some updates. So thank you so much. We really appreciate you coming here and sharing your time with us.
Thank you so much for the invitation. It really was a pleasure. I just wanted to add, I think somewhere my contact information is shared. I'd be happy to, take the discussion offline. I noticed there were some questions in the chat. So yeah, please feel free to send me an email. We're always happy to talk about the things we enjoy working on. Thank you so much.
Wonderful. Thank you. And thanks everyone for coming, asking really interesting questions. It's always more interesting. And yeah, if you like discussions like this, our next talk will be with Dr. Wallace Colomer, talking about the human microbiome transmission landscape. So basically, how we humans transfer the human microbiome and how these patterns change in different populations. So thank you so much, and I hope I hear you all back again. Thank you. I'll close the room in 3, 2, 1. Bye everyone. Thank you.